All right. So a secant is a line. I'm giving you the simple definition. A line that intersects a curve twice. All right. Now, really, I mean, the geometric definition is a line that originates at a point outside of a circle, intersecting the circle twice at the circumference. All right. I mean, it works to that effect. I mean, it's kind of like a lot, but what we need is this concept extended to function math, which would not incorporate the idea of a circle, at least not yet. What we're talking about is some curve. Oh, that's not a curve because it let it autocorrect. Some curve that exists in such a way that a line is intersecting that curve at two distinct points. So this would be a secant. All right, what we need to figure out is the slope of the secant line. All right, so I'm going to overlay this on a set of coordinate axes. And so I'm just going to pull some axes in here. Should be good. Actually, I don't even need the numbers. Oh, okay. Well, if I'm doing that, I'm just drawing two lines. I don't even need the calculator for that. So I'm going to pop in a y-axis and an x-axis. Put this stuff back on for later. All right. So what we want to do is find the slope of the secant line, but we want to find it in general terms. Okay, so I'm gonna designate two arbitrary points, one of which I'll call A, and the other of which I'll call B. All right. Let me just hang on to this diagram. I'm going to draw it again in a sec. So every coordinate in space has an x value, comma, y value. We're designating this as the function y equals f of x. So the y value is f of x, f of whatever the x value is. All right. So one way that I can designate a point in space is if I were to say, here's a set of coordinate axes, here's one, and I have some function, f of x. Normally, I would say it's x comma y, but in this case, the x value is equal to 1, y, right? And if I say y is equal to f of x, then I'm saying 1 comma f of x, but the x value is 1, so 1 comma f of 1, right? So this is just a quick side example here. All right, to justify why I'm about to call this a comma f of x. All right, because it's always x comma f of x, x comma y, but y is f of x. So if I tell you that the x value is a, then it would necessarily have to be f of a instead of f of x. All right, so my second coordinate, b comma f of b. All right, now slope in general is just changing y over changing x. It's actually pretty simple. I mean, you've been doing it for years. That's not an exaggeration. Right? Rates of change have been with you ever since the beginning. So if I want the slope of the secant, I'd be looking at change in y over change in x. All right, my y values are f of b and f of a. So the change between those would be f of b minus f of a. Then I would have the change in the x values in the same order would just be b minus a. All right. So if I want to evaluate a particular function in order to find the slope of the secant line, I can do it a bunch of different ways. I could do it completely manually, but what I could also do is put the function in and find the y values that correspond with those x values, and then go from there. So I'll just get a quick sketch of what y equals x cubed minus x looks like. All right, so it looks like that. What they're saying is over the interval of 1 to 3. So here's 1, where is 1? 1's right here, here's 1, coordinate 1, 0. All right, so I can snag that from here. I can also pull out 3. I mean, it'd take a little doing, but I can get there. So, you know, just kind of going up the line here till I get to 3, seeing what y value that corresponds with. You know, if it'll let you, but in this case it does. 3 gives you 24. So f of 3 is equal to 24. All right. So if I tell you that this is the a value and this is the b value, all right, then I'm saying that this is f of the a value, and this would have to be f of the b value. So the slope of the secant line which is change in y over change in x, would be f of b minus f of a, so 24 minus 0, over b minus a, 3 minus 1, 24 over 2 gives you 12. All right, and that would be the slope of the secant line. All right. But there's another way that we can write the slope of the secant line. So I'm going back to my diagram here. Instead of choosing a second point that we call B, what we can do is we can relate the second point to the first point, but we would have to do so by determining what that relationship is. All right. So what we would say here is that we're starting off at A. I'm going to bring it in. We're starting off at A and then making some kind of horizontal movement that we call H to get us to a point that's either above or below my second point. And it could actually be on the second point, but we don't expect that to be the case. All right. So what we would end up with here is a new location, A increased by H. All right. A increased by H. So if this point is A comma F of A, then this point would have to be A plus H comma F of A plus H. All right. And as long as you have two coordinates, you can come up with your slope of the secant definition. Because the slope of the secant is just a change in your y values divided by the change in your x values. So change in y, f of x plus h, a plus h, minus f of a, the two y values subtracted, over a plus h minus a. But you see we have an a and a negative a, they would cancel each other out. And so you would end up with, you should possibly be familiar with this. It comes up in pre-calc. Maybe you're familiar with this because you liked it. It was one of the things that you liked the least in pre-calc, but this is the difference quotient. F of A plus H, you know it as F of X plus H. I'll explain how we transition from one to the other in the next class. But F of A plus H minus F of A all over H. Right. And so that would also be a way in which we can determine the slope of the secant. Right. So I will tell you that I took the liberty of putting together, get rid of this, make sure I save this, a difference quotient Desmos, so that for rote cases where you actually have to compute the difference quotient, you can just do it with a calculator. So it's on Blackboard, it's there already, but I put both difference quotients in. You put your original function. So if we go back to example 1, x cubed minus x. All right, I have a line segment created. I think it kind of looks nice. Indicate what your A and B values are. So 1 and 3. It'll plot the points for you. You know, it's kind of hard to see if you don't zoom it, the right way, but you can see a line segment is created there on the graph. I can even turn it off if I want, right? Just by turning off the whole folder. But I have my points and I have my lines, and then you can see the difference quotient is computed for you by the rule, by the formulas. In both cases, give you a 12. So that would be the end of it, right? So what I'll ask you to do is have a look at example 2 and example 3 for next class, because we'll start off next class with these 2 examples, and then we'll get into the concept of a derivative, the limit definition, and then we'll get into some derivative shortcut rules and all the fun stuff that a lot of people have been waiting for. So I'm going to stop the recording.